What if you walked up to a 1600-year-old iron monument, ran your fingers across it, and found no rust? No flaking? No deep orange scars, just dark, smooth metal holding its shape like time forgot it. And then you realize this isn't a museum trick. It's outdoors, in humid air, through monsoons, through centuries of smoke and dust and fingerprints. So the question stops being, how is it still standing, and becomes something stranger. What if ancient people figured out a way to make iron that practically refuses to rot? You can go to Delhi and see it, the Iron Pillar. It stands over 7 meters tall and weighs several tons. It was likely erected during the Gupta period, often linked to Chandragupta II, around the 4th or 5th century CE. It has an inscription, it has history, and it has something that feels like a glitch in the rules. Because iron rusts, that's the deal. Give it oxygen and water and enough time, and it turns back into something closer to rock. Modern cities spend billions trying to slow that process down, paint it, plate it, wrap it, replace it. But this pillar was never wrapped, it just endured. At first, you might think the story is exaggerated. Maybe it's not really iron. Maybe it's coated with something. Maybe the air in Delhi is unusually dry, except Delhi isn't a desert. It has long, humid seasons, heavy rains, and huge temperature swings. Plenty of perfect rust weather. And the pillar isn't the only case people point to. Across India, there are ancient iron objects, tools, clamps, beams, some in temples, some buried, some exposed. Not all are rustless. Many are corroded like you'd expect, but enough examples survive in suspiciously good condition to make you lean in. So you start building a hypothesis in your head. Maybe ancient Indian metalworkers had a lost technique, a recipe, a ritual, something that doesn't fit our timeline of primitive metallurgy. You learn that India had deep knowledge of iron early on. High-quality steel known as wrought-iron was produced in South India and exported widely. Wrought-iron became famous centuries later because it fed the legend of Damascus steel, blades with hypnotic patterns, and a reputation for toughness. The process involved carefully controlled carbon in crucibles, producing steel that could be both hard and resilient. That already tells you something. These weren't accidental blacksmiths. They were chemists with hammers. Then there's the scale. The Delhi pillar isn't a small artifact. It's a massive forged object, not cast in a mold, but built by welding and hammering lumps of iron together. That means planning, heat control, and a supply chain of fuel and ore. The kind of industrial choreography you don't expect from the ancient world. And there's the composition. Analyses have shown the pillar is made of wrought iron with relatively low carbon, but it contains higher phosphorus than many modern steels. It also has very low sulfur and manganese, which matters because those elements affect how iron behaves during forging and corrosion. So now your theory takes shape. Maybe they discovered a natural corrosion-resistant alloy, not by adding chromium like stainless steel, but by doing something subtler, something that lets the surface protect itself. Because rust isn't just rust. Corrosion can be a slow, layered chemistry. Some metals form a tight, stable oxide layer that shields what's underneath. Aluminum does this. Titanium does this. Stainless steel does this with chromium. If iron could form the right kind of skin, it might last far longer than you'd expect. And then you hear about a strange film on the pillar's surface. A thin layer that isn't the loose, crumbly rust you see on abandoned cars. It's more stable, more adherent. Almost like the metal is wearing armor made from its own decay. The more you investigate, the stranger it gets. Because this isn't just metallurgy. It's environment, chemistry, time, and chance all braiding together. Delhi's climate cycles between wet and dry. Corrosion often accelerates when metal stays wet for long periods, but if the surface dries quickly after rain, the chemistry changes. Now imagine centuries of this. Brief wetting, then drying, again and again. Like a slow laboratory experiment run by weather. Then consider what the pillar has been exposed to. Smoke from fires, organic acids, dust, bird droppings, human touch, maybe even oils used in rituals. Each one could alter the surface chemistry by tiny amounts. Over hundreds of years, tiny amounts become a layer. And the pillar may have started life somewhere else. Many historians think it was moved to Delhi from another location. If it spent early centuries in a different climate, that first skin could have formed under conditions we can't fully reconstruct. You start noticing coincidences that feel like fingerprints. High phosphorus can encourage the formation of certain iron oxyhydroxides. In particular, researchers have pointed to a compound called mesawite, a form of delta-FeOOH, and the presence of iron hydrogen phosphate compounds in the protective film. The idea is not that phosphorus makes iron magically immune, but that it nudges the corrosion into forming a dense, compact layer instead of a porous, flaky one. And the pillar's forging method may matter too. Traditional bloomery iron making and forging can leave slag inclusions, tiny non-metallic particles, distributed through wrought iron. Those inclusions can influence how corrosion proceeds, sometimes acting like microbarriers or guiding the growth of protective layers. Now the hypothesis starts to feel almost plausible. Maybe ancient India accidentally engineered a self-protecting iron by using phosphorus-rich ore, low-carbon wrought iron, careful forging, and a climate that cured the surface over centuries. So you go looking for people who have tried to solve it without myth. Metallurgists and archaeometallurgy researchers have studied the Delhi iron pillar for decades. The Archaeological Survey of India has documented it. Analyses have been published in journals like Corrosion Science. A well-known study by Balasubramaniam, a professor at IIT Kanpur, examined the pillar's composition and argued that the protective layer is key. He described how phosphorus, slag inclusions, and environmental wet-dry cycles could produce a stable passive film containing iron oxyhydroxides and phosphates. Other researchers have examined similar ancient Indian irons and found that corrosion resistance varies widely. That matters. If it were a lost universal method, you'd expect consistency. Instead, you see a spectrum, some objects heavily corroded, some strangely preserved. That suggests conditions and details matter. A lot. You also learn what the pillar is not. It's not stainless steel. It doesn't contain high chromium. It's not a modern alloy that time-traveled. It's plain iron, but with an uncommon chemistry and an uncommon history. So for a moment, it feels like you're close to the secret. Like the ancients had a formula we forgot, and the pillar is the proof. And then comes the twist. Most experts don't think there's a single, rustless recipe at all. They think the pillar is a perfect storm. Iron does corrode on the pillar. It's just extremely slow, and the corrosion products are unusually protective. When people describe it as never rusted, they're simplifying. The surface has changed. The difference is that the change didn't destroy it. And a major reason could be something almost disappointing. The pillar is thick. Mass matters. Corrosion is a surface phenomenon. If you have a massive object, you can lose tiny fractions of a millimeter over centuries and still look intact. A thin iron sheet would be gone. A giant pillar can take the hit. Then there's human intervention. The pillar has been cleaned. It has been studied. It has been touched by countless visitors. Over the centuries, it may have been sheltered at times or protected indirectly by structures around it. Even small changes in exposure can change corrosion rates dramatically. And the ancient secret of phosphorus isn't a secret in the mystical sense. It's chemistry. Phosphorus ended up in the iron because of the ores and smelting practices. Ancient furnaces often didn't remove phosphorus the way modern methods do. Modern steelmaking generally tries to reduce phosphorus because it can make steel brittle in certain contexts. So we didn't forget the ingredient. We intentionally avoid it for many applications. In other words, the same fact that sounds like a magical alloy, high phosphorus, might just be a byproduct of older technology and local geology, not a deliberate breakthrough aimed at corrosion resistance. And the climate argument cuts both ways. Delhi's environment today includes pollution that can actually accelerate corrosion, especially with sulfur compounds and particulates. If the pillar is still doing well, that's impressive. But it also means the early formation of the protective film might have occurred before modern industrial air. Or the film is tougher than current conditions can easily break. Now the story shifts. Not ancient supermetal, but ancient iron that got lucky and then got armored by time. Except that explanation isn't fully satisfying either. Because if it's just thickness and luck, why does the pillar have such a specific kind of protective layer? Why do phosphates show up in the film? Why does the corrosion behave more like passivation than decay? Why do some parts of the pillar corrode more than others, depending on exposure and microstructure? And if it's mostly environment, why don't we see the same effect on every old iron object sitting outside for centuries? Why aren't cities full of accidental rustless relics? So you end up in a final conflict between two imperfect stories. The romantic story says, ancient India had a method, and we lost it. But that story struggles to explain the variability across artifacts, and it risks turning complex science into a single mystical key. The mainstream story says, it's understood phosphorus, slag, passive film, wet-dry cycles, and the sheer mass of the pillar. But that story still has gaps. It can describe what's there and propose mechanisms, yet it can't rewind history and rerun the experiment cleanly. You can't recreate 16 centuries of weather. You can't perfectly reproduce the ancient furnace conditions, or impurities, forging rhythms, and the pillar's early life. Even when researchers make modern irons with controlled phosphorus and test corrosion, real-world time is the missing ingredient. Corrosion is a slow conversation between metal and environment, and the environment never speaks the same way twice. So maybe the most honest answer is also the most unsettling. The pillar doesn't prove ancient people had impossible technology, but it does prove something else. That progress isn't a straight line. Sometimes knowledge is gained, sometimes it's bypassed, sometimes it's intentionally discarded, and sometimes it's hidden inside side effects we don't value anymore. When you stand in front of that dark iron surface, you're not just looking at a metal object. You're looking at an event that's still happening: atoms trading places, films forming, layers tightening, tiny losses accumulating so slowly your lifetime can't measure them. And that's the real wonder. Not that the iron never rusted, but that time tried to destroy it in the most ordinary way possible, and the ordinary rules weren't quite enough. So the next time you see rust on a railing or a bridge, you might feel like you understand metal. It decays, end of story. But somewhere in the chemistry between rain and sunlight, between ore and fire, there's a narrow path where decay becomes protection. And it leaves you with a question that doesn't belong only to metallurgy. How many lost secrets are not secrets at all, but moments when nature and human craft briefly aligned and made something that could outlast the people who named it?